With geometric isomers, when we have a double bond, we have a pi bond, and that pi bond is going to prevent rotation around that center, unlike when we have single bonds, okay, that carbon-carbon bond, we can rotate around that. So whatever's attached to those carbons, we can change the configuration or the conformation of those around those carbon centers. But when there's a pi bond, that's not possible. So whatever's attached to those vinylic carbons, that's what those carbons are referred to as, their positioning, whether they are catty-corner to each other, or if this were, let's see if I can do it easily here. Okay, not so easily, but if this one were down here and they were on the same side of the double bond, that's going to give us a distinctly different compound. And so we call these geometric isomers, atoms that are bonded in the same order, but they just have a different spatial arrangement around the double bond. And they're different than some other isomers that vary only in the arrangement of the particles. They belong to a broad category called stereoisomers. And so when we are looking at and naming these, we need to focus on the carbons of the double bond, namely we call them the vinylic carbons, and then consider everything that's coming off of those carbons. Even if they're part of the parent chain, we need to consider them like substituents for purposes of determining the naming and what we call the priority of the group. So looking at and thinking about isomers, we know that isomers have the same molecular formula, but they are distinctly different compounds. We've looked at constitutional or structural isomers before, where we have the same molecular formula, but the way that the atoms are connected to each other is different. Stereoisomers are another type of isomer, and this is where they have the same molecular formula, they have the same connectivity of the atoms, but spatially how those atoms are arranged relative to one another is different. And there's a couple different categories of stereoisomers without getting too deeply into it. When you have stereoisomers, or when you have formulas that have the same molecular formula, same connectivity, and they are mirror images of each other. So a good example is your hands, okay? Your hands are mirror images of each other, but if you try to superimpose them, notice they don't match up. Okay, that's molecules that are like that, mirror images of each other but are not superimposable. Those are called enantiomers. When you have stereoisomers that are not mirror images of each other and they are not superimposable, then you get what we're called diastereomers. And so depending on whether we're talking about enantiomers or diastereomers, there are different ways that we can name and identify the stereoisomerism that's taking place. In this video, we're going to take a look specifically at the diastereomers and what happens when we have double bonds and we substitute onto those vinylic carbons, and how we're going to go about naming those kinds of alkenes. Now, the first type that we're going to look at is what we're going to refer to as di-substituted alkenes. And what we mean by that is, so if this is the carbon-carbon double bond, and imagine for a moment that this was just ethene, okay, so it had hydrogens on, 2 hydrogens on each of the carbons. Well, if I substituted 2 of those, 1 on each of the carbons, okay, and put on, say, a methyl group, then I would have this turns into a 4-carbon parent chain, but this would be a di-substituted alkene, okay? Now, di-substituted alkenes, we can also apply this to when we have a ring structure. We have a cycloalkane, and we substitute for some of the hydrogens that are on there. We know that cycloalkanes and alkenes will have the same generic formula, CnH2n. And so when we have carbons that are in a ring structure, like with the cycloalkanes, that ring structure is also going to inhibit the ability to twist around any given single bond. And so the arrangement of any substituent groups now makes a big difference and leads to a slightly different name for that compound. And so the cis and the trans identifiers are used to indicate the relative position of those substituent groups. When your groups are on the same side of the ring than they are in the cis configuration. When they are positioned opposite one another, okay, on opposite sides of the ring, or catty corner if you want to think of it that way, that would be the trans arrangement. So you can see that both of these are 1,2-dimethyl cyclohexanes, but the difference is how are those methyl groups arranged. The one on the left would be cis 1,2-dimethyl cyclohexane because both methyl groups are on the same side. The second one would be trans 1,2-dimethyl cyclohexane because the methyl groups are on opposite sides of the ring. The same sort of thing happens, all right, when we look at an alkene. Okay, so first of all, our parent chain is 4 carbons, okay, longest continuous chain that contains the double bond, and it's on carbon 2, so it's a 2-butene. But notice the difference between these two structures. If you imagine a line that goes through, that runs parallel to the pi bond, okay, then you can see these methyl groups are on the same side of the double bond. So that would be a cis arrangement, kind of like they were on the same side of the ring. In this one, they are on opposite sides of that imaginary line. So this would be the trans arrangement, and this would be trans 2-butene. So if we take a look at this example, we can see that there are 3 different double bonds in this structure. And so we want to be able to analyze each double bond and determine, is it in a cis arrangement, a trans arrangement, or is it not even a stereoisomer at all? And so if we consider each one, again, we look at this first one here, and if we imagine the imaginary line going parallel to the double bond, we see that on each of these carbons, the carbon groups coming off of them are on the same side. So that would be a cis arrangement for that one. All right, if we look at the next one, going from left to right here, this one up here, okay, this is our imaginary line. And if we look at the carbon groups that are coming off of those vanillic carbons, we see that they are on opposite sides, and so therefore that would be considered a trans position, okay, or a trans orientation. If we look at this one though, and we think about what's attached to this terminal carbon here, well, we know that hydrogens are not shown and there's no formal charges, so we're assuming that there's going to be 2 hydrogens there. And if we think to ourselves, well, if I draw my imaginary line here, if I switch these hydrogens, switch places, there's nothing different there, okay? So therefore, there is, because you have the same group coming off of the vanillic carbon, in this case, we don't have any stereoisomerism at all. And so that's one of the things that you have to keep in mind also, is that whatever's attached to the vanillic group, they have to be different groups from each other in order for this stereoisomerism to occur. So what happens if our alkene is not just di-substituted? What if it has 3 of the hydrogens substituted, or even 4? When we have tri or tetra-substituted alkenes, then we have to get into another system of nomenclature known as the EZ nomenclature. It's once you get used to it, it's easy, but the E and the Z have a different root word for that. But we use these when we have more than just 2 substituted groups on the vanillic carbons. And so what we want to do is look at those carbons that are attached to the double bond, the vanillic positions, and we have to determine, connected to each of those carbons, which group has the higher priority. And what do we mean by that? Well, in order to determine priority, we have to look at what's connected to the vanillic carbon and work our way outward until we find a point of difference. And what we use to determine that priority is the atomic number of the atoms that are bonded to them. If the first atom out doesn't provide that difference, then we continue working our way outward until we find a point of difference. So once we've determined on each of the vanillic carbons which group has the higher priority, if your high priority groups are on opposite sides of the double bond, so what we would have called a trans orientation for a disubstituted alkene, then that gets the designation E, and that E stands for entgegen. All right, that refers to opposite sides. If, however, your high priority groups are on the same side of the double bond, then that gets a Z designation, the letter Z coming from the German word zusammen. And so an easy way to remember that is if your high priority groups are on the same side of the double bond, then it gets a Z designation. All right, so if we take a look here, again, we see our structures are oriented with the double bond as the focal point. And so drawing that line there, okay, allows us to consider the left-hand vanillic carbon and the right-hand vanillic carbon. On the left, we see that that carbon is attached directly to a hydrogen up top and the carbon on the bottom, okay? Well, if we compare the atomic numbers, carbon has atomic number of 6, hydrogen is 1, so the CH3 group in the bottom left, that's the high priority group on the left-hand vanillic carbon. On the right-hand vanillic carbon, the first atom out is a carbon in both directions. So that's not going to, give us any information. So then we have to look beyond that. The lower carbon is attached to 3 hydrogens. The upper carbon is attached to the next carbon and 2 hydrogens. So because that first atom out, okay, actually it's the second carbon out, or the second atom out from the vanillic carbon position, okay, the top structure takes precedence because this carbon is attached to another carbon, whereas the bottom carbon is only attached to 3 hydrogens. So the high priority group is the one on top. Now we consider the imaginary line, if you will, okay, that runs through the double bond, and our high priority groups are on opposite sides of that double bond line, and so this would be entgegen, so it would be E, notice it goes in parentheses, 3-methyl 2-pentene. If we look at the second structure, again, split that down the middle. On the left-hand vanillic carbon, the lower group is the high priority group. This time, though, the 2-carbon group is on the bottom, and so that is still our high priority group, but now notice the difference in the positioning. They are on the same side of the double bond. They're both on the bottom here in this drawing, and so this would be labeled as Z 3-methyl 2-pentene.